Great. Thank you, everyone. I'm Keith Hawkins. I'm an associate professor of astronomy at UT Austin, but I was a graduate student here with Jerry Gilmore between 2013 and 16. And what I'll be discussing is, and Alice set it up beautifully, is galactic archaeology and cartography, although we'll see if I can get to the cartography part, in the Gaia era. And so I found this picture of Cambridge actually with the Milky Way and thought this is a great image to start with. I had to actually look to see if it was real. And it turns out it is real. And it's images like this that got me excited about whether, how do galaxies like this Milky Way, how does it assemble and form and evolve over cosmic time? And how do you also structure a galaxy like the Milky Way? And these questions, right, about galaxies in general as galaxy evolution and formation, but answering these questions in the context of and using the Milky Way as a laboratory is really what galactic archaeology is all about. And so when I was in the US, I was basically told that like in the US, cosmology and exoplanets were the two big fields, and in Europe it was stars and Milky Way. And so I applied for a Marshall Scholarship and came to the IOA to study in 2013 because it was just, everything was so exciting at the time. And so this particular talk, I'll try to highlight three things. One is that the IOA has been a powerhouse and is a powerhouse in galactic evolution and archaeology. The second is that the tools of galactic archaeology, the chemodynamic cartography or the chemodynamic mapping and tagging that Alice kind of discussed, and the cartography has kind of been refined and honed here at the IOA and beyond. And that I think there's a bright future for galactic and stellar archaeology in the IOA and beyond because of the large spectroscopic and astrometric surveys like Gaia, JWST, ELT, and so forth. But I'll start with this first one, and I probably won't spend too much time on this, but I at least thought it would be nice to say some of the history that has happened here in the IOA in galactic archaeology and evolution. And I did this with a pretty simple timeline that I've only highlighted one thing in each decade. Of course, this is completely not exhaustive. This is just for illustrative purposes, just to give you a sense for the rich history that has happened here at the IOA. And so if you sit down and think about, like, if you go back into the early days and ask, what is the theories for galactic evolution, galactic formation, some of the kind of the seminal papers were, monolithic collapse, which is, this idea that galaxies form by large collapse of gas clouds from ELS, so Egan, Linden, Bell, and Sandage in '68. If you go one decade later, right, this idea of galaxies forming through accretion of smaller subgalactic systems that Alice discussed was from Cyril and Zinn in '78, although White and Rees wrote a beautiful seminal paper as well here at the IOA in '78 on this topic as well. And then if you fast forward to the '80s, we started learning about our own galaxy and the structure of it when the thick disk was discovered by basically stellar cartography, by basically mapping the number density of stars vertically through the galactic disk in the '80s from Gilmore and Reed. If you fast forward even further, we get even further evidence for the hierarchical assembly formation picture by the discovery of the Sagittarius Dwarf Galaxy in the '90s by Abada. And then this was kind of more completed as if you were by the field of streams by Vasily in 2006. And we kind of entered in the early 2000s this very industrial revolution in galactic archaeology where the sample sizes were going from maybe a few hundred stars or a few thousand stars to something like 1 million stars at a time. And this kind of led to things like the large spectroscopic survey, the Gaia survey from Gilmore, and the Gaia satellite being launched here in 2013. And I stopped this at 2013 in part because that's when I started. All of this rich history going on here is what drew me, I think, to the IOA, to the other side of the pond, to really study and explore the Milky Way. And now we're continuing this industrial era. We have these large spectroscopic surveys like Gaia and Apogee and Rave that have already been completed, but we have a large number of future and ongoing surveys like Sloan 5 that I'm the spokesperson for, or Gaia and Weave and Foremost and Lamost and HETDEX. HETDEX, for those of you who are unaware, yes, it is a dark energy experiment, but it accidentally observed like a quarter of a million stars that we're actually doing abundances for now. And this is partly why the Decadal Survey has called this the key discovery area in this particular subdiscipline of astronomy. Of course, if you're interested in studying the Milky Way as a laboratory for galaxy formation and evolution, there are some problems here, right? That we live inside the Milky Way, so we have a skewed perception of what the Milky Way actually looks like. And as Alice kind of beautifully illustrated, the Milky Way is really just a jumbled up mess of stars that have been born in associations and clusters that have dissolved and phase mixed. It's also stars that were born in one radius and then completely dynamically moved around thanks to accretion events or co-rotation resonances or other resonant dynamics. And it's stars that were born in completely external systems that have been fully disrupted and are now inside the Milky Way. And so one might ask, well, how can you even uncover the assembly history of the Milky Way if it's just this jumbled up mess of stars? And for a galactic archaeologist, like any archaeologist, we have tools to do this. One is dynamical tagging that Alice discussed, and one is chemical tagging, which was actually highlighted in a question, which I'll talk a little bit more about. And one is chemical cartography, which I hope to get to, but I may not. So I'll start with chemical tagging, and this really goes into that second theme of my talk. So the goal of chemical tagging is, this idea came around in the early 2000s by Freeman and Bland Hawthorne, and the goal essentially is to determine the birth location and time of a star with its chemistry alone. If you can do that, right, it's kind of like DNA tagging for human beings, right? So you can tell if I take a DNA test, a certain part of my ancestry comes from Africa, a certain part comes from Europe and so forth. Imagine doing that for stars using the chemistry as the DNA tag. You can do this because the chemical composition of the star's surface, generally speaking, doesn't change a whole lot over its lifetime. And so embedded in that chemistry, the detailed chemical abundances, is the kind of the history of when and where it was born in the galaxy or in another galaxy. And so if you can do this, you can actually pull apart and actually back out the accretion history of the Milky Way. In order for this to work, there are two requirements. One is that stars that are born together, like binaries or open clusters or dwarf galaxies, have to have similar chemistry because that's the tag you're going to use. And stars born in one location have to be chemically different than stars born somewhere else. They have to be uniquely different. And so we actually asked, this is a good question, right? Does chemical tagging actually work? And you can ask this by asking, are the requirements satisfied? So people have done this, and this is an example from Semyoung Oh's beautiful paper on Kronos and Krios, where they ask the question, are wide binaries chemically homogeneous or not? That's the underlying requirement for chemical tagging to work. The chemistry that you're seeing here is the X/H ratio for stars, the X/H ratio for two wide binaries, one in red and the other its companion in blue for different elements. The red and blue lines should overlap if this chemistry of wide binaries is homogeneous. Unfortunately, they don't. This is really bad news for chemical tagging. And so there was a lot of questions about whether or not this was just a fluke or is this actually normal for stars that are born together to disagree in their chemistry. Huge amount of literature on this. I don't have time to talk about it, but I did want to highlight some of the work that's been done on this. And so this kind of made us rethink, does chemical tagging work or does it not work? And if you ask this question to the literature, you'll get two different answers. Laia Casamaquela writes a paper in 2021 saying that they looked at open clusters and you can't distinguish them chemically, so chemical tagging won't work. Then Spina writes a paper in 2022, 6 months later with Gaia ESO data and says, actually it can. So the literature is completely confused on this. And so we decided that we would try to test whether chemical tagging can work by looking at the underlying assumptions, basically taking wide binaries, going to McDonald Observatory, observing them in high resolution, and doing the chemical test of whether or not this Kronos and Krios pair is a fluke or if it actually happens regularly. So we essentially do high resolution spectroscopy of, this is an example of high resolution spectra of 4 different wide binaries. One spectrum is in solid, one spectrum is dashed. You almost can't see any difference between the two spectra, which tells you that by and large, the chemical homogeneity of wide binaries they're pretty homogeneous, right? It's most likely that the Kronos and Krios pair was likely a fluke. This is our summary plot from that particular paper where we show that the dispersion of the difference in the abundances on the x-axis for the wide binaries is red triangles compared to the errors. We just don't see a difference in the errors, but we can actually measure quite a large difference with random pairs of field stars. So it turns out that in 85 to 90% of the pairs that we studied, they're exactly chemically homogeneous, which is fantastic for chemical tagging. This got some press because I myself am not homogeneous with my twin brother, Kevin. We extended this work with a larger sample of wide binaries, and we actually pushed it out to much further separations to really ask, does the delta of metallicity, right, does the metallicity difference between the wide binaries change as you pull the stars apart? The answer is yes, it does change. Things get a little bit more dishomogeneous, inhomogeneous as you move to further and further pair separations, but by and large, things remain homogeneous. And this was followed up actually in 2024 with a nice paper by David Young, who shows that this is the 3D pair separation as a function of the 3D velocity difference between wide binaries, showing that as long as you stay within 10 to the 6 AU, things are pretty homogeneous. And that 10% and they also show that this is about 10% or so of the stars are not homogeneous. So what's causing those 10% of stars not to be homogeneous? There was a nice Nature paper by a similar team, which says that that's actually due to planetary ingestion. So by and large, we think chemical tagging can work. The first requirement is at least satisfied by and large. The other requirement is whether two stars that are born in different locations are chemically similar or not. And this is essentially asking the question about the doppelganger rate. Is the chemical doppelganger rate low? That is to say, are two stars that are born in completely different places chemically identical? Because if they are, then that actually will kill chemical tagging as an option. We actually did, I don't have time to talk about it, but we did do some work in my group with Catherine Minea, who graduated a couple of weeks ago in my group and moving to Columbia as an NSF fellow, where she actually looks at the chemical doppelganger rate with heavy elements and finds that it's well below 1%. So I think that things are looking good there. So chemical tagging can probably work to some degree at least, and so it's a pretty powerful tool to use chemodynamic tagging, as Alice kind of mentioned, to actually explore all of the phase mix distribution, the phase mixed items like dwarf galaxies and disintegrated clusters that have built the Milky Way. I'll just give a couple of examples of chemical tagging in action. For example, this was from 2015 when I just joined Jerry's group, where Karen Lind actually used the Gaia survey to study the detailed abundances of stars, and found that she found a star in the galactic halo, or sorry, in the galactic field population that had this weird aluminum abundance, very, very high aluminum abundance, and very low magnesium abundance. We only see that in globular clusters, and this actually allowed Karen to figure out that there was a star that had been disintegrated from the Omega Cen globular cluster. And you can actually use chemical tagging to, for example, determine what is the fraction of stars in the Milky Way's, for example, the Milky Way's bulge, that have come from disintegrated dwarf galaxies that have built, for example, the bulge. And so my student, Maddie Lucy, who's now an NSF fellow at UPenn, actually did this in the Combe survey, where she basically redid Karen's paper, but then did it in the interior parts of the Milky Way to ask what is the fraction of the interior part of the Milky Way that actually has come from disintegrated dwarf galaxies. Another example of chemical tagging in action, an IOA-specific example, is in 2015, I actually, when I was here as a PhD student, developed a chemical plane in aluminum, magnesium, and manganese that could help distinguish stars that are accreted from dwarf galaxy systems, potentially fully disintegrated dwarf galaxy systems, and the Milky Way. So this is that plane from Pyle Daz's work, where you can actually separate out the thin disk, the thick disk, and this accreted halo material that was way offset in aluminum, or aluminium, as it's called here. This actually helped, in some sense, Vasily and others discover the Gaia Enceladus sausage. People have actually gone further with this. Danny Horta's work in 2022 actually used this chemical plane to discover other accreted systems like the intergalactic structure and so forth. So this is an example of how chemical tagging can be used to find accreted systems. And I think there's a lot of future prospects here because you can actually do this, when people are starting to do this, in M31. An example of that is David Nidever's work on looking at individual stars with JWST in M31 to really tag its formation and assembly. Okay, so tagging tells us about the accretion history, but doesn't really tell us a whole lot about its structure. To do that, you need cartography, and in the last 2 to 3 minutes, I'll just very quickly talk about some of the work we're doing in cartography. And so the question that I'm interested in answering with cartographic studies is how the galaxy is structured, and in particular, how the elemental elements in the galaxy are spatially distributed in R and Z, well, beyond R and Z actually, because that tells us about the structure of the Milky Way. So for example, let's start out with a simple toy model. Let's say you have the inner part of the Milky Way is metal rich, and as you go out to the outer galaxy, it stays the same metallicity. This would imply there's no metal gradient in the galactic disk. If we observed this in the Milky Way, this would imply that the gas that formed the Milky Way was extremely well mixed, and so the inner part and the outer part had the same chemistry. And so that way you'd see no gradient at all. So this tells us about, this cartographic study would tell us about the formation of the Milky Way, or at least the process in which the Milky Way was created. If, however, the inner galaxy is metal rich and the outer galaxy is metal poor, and you see a negative metallicity gradient with radius, that would imply inside-out formation, that the inner part of the galaxy formed chemically very quickly, and the outer part was kind of lagging behind a little bit more slowly. And so people have done this. Oh, and I should also say the assumption here is that all of the stars at a given radius have exactly the same chemistry. So people have seen this metal gradient in the disk, negative metallicity gradient in the disk, first observed, one of the first papers I can find was Jane's 79 that did this in open clusters. And they show a negative metallicity gradient implying inside-out formation. And this is what's kind of routinely discussed in the literature. And this has also been done in field stars, a metallicity gradient of minus 0.05 dex per kpc from Mayor. Surprisingly, with just 600 stars, they actually do this, and we do millions of stars now, and we see the exact same result, which is great. And so one of the things that people assumes is that the chemistry at any given radius is exactly the same, right? At any given radius, the metallicity is, say, 0. And so one of the things we were interested in is, well, are there azimuthal variations in metallicity across the disk? Because that will tell us more about how, for example, the disk is structured. And we're in now with Gaia and all these large spectroscopic surveys, we're in a place to actually test that. Why we might think it's not is because we've actually seen, at least in gas, this is from Manga, that in gas there are actually azimuthal metallicity variations in gas in external galaxies, so it stands to reason there may actually be azimuthal variations in metallicity in the galactic disk, even though people haven't really checked. So we went out and checked it, and we basically took a large spectroscopic survey, we measure the metallicities in that large spectroscopic survey, and then we map the spatial distribution of metallicity across the disk, not just in radius, but also in phi. How much time is left?
0.
Oh. I'll just show you the result from that, which is that we basically find that there are azimuthal metallicity variations and that they align with the galactic disk. And since there's 0 minutes left, I will skip the press release on that and basically say that we don't know why they're being caused. We're trying to figure that out now. And leave up my summary.